Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about the module Wave Packets in Space and Time under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. Firstly, we'll try and know how the superposition of plane harmonic waves of different wavelengths or wave numbers can produce a wave packet localized in space. Then, we'll learn an important criterion for localizing a wave packet describing a particle in space. Thirdly, we'll know the superposition of harmonic waves of varying frequencies or angular frequencies can produce a localized wave packet in time. Fourthly, we define the group velocity of a wave packet and show that it is in agreement with the classical expression of a particle. That means that the group velocity of the wave packet actually describes the particle velocity of the particle with which the wave packet is associated. And finally, we'll analyze the evolution of a wave packet in time and show that the spread of the wave packet increases with time. Having studied the concept of wave nature of matter in the preceding module, we turn over to discuss in this module the question of how to describe localized particles of matter using de Broglie hypothesis. We have seen while studying the quantum properties of atoms that the classical picture of a particle in terms of a point object having a precise position and momentum at every instant of time cannot hold, at least in its entirety in the atomic domain. So, in this module, we shall see that while a pure harmonic wave of a definite wave number is known to extend over all space and cannot be used to locate the position of a particle because of the fact that it is extending over the entire space, we need to have another concept associated with the wave function which can tell us exactly or at least approximately where the particle is localized. We can consider a superposition of harmonic waves of different wavelengths to obtain such a localized wave packet that will describe the position of a particle. Similarly, superposition of a number of harmonic waves of varying frequency or angular frequencies will also produce wave packet in time which is localized and which again can give us a localized position of the particle. We shall also analyze the evolution of a wave packet in time and show that the spread of the wave packet increases with time. Now, coming on to the description of a particle by superposition of harmonic waves. So, a plane harmonic wave of a single wavelength is known to spread over all space, which in other words means that while the wave function of the particle depicts or denotes the wave nature of the particle, however, it is not sufficient for us to know where the particle is localized in space because the wave function extends over the entire space. Therefore, it is imperative to describe a localized particle in space, and this we can do by having a superposition of a number of waves of different wavelengths. Such a superposition of waves of different wavelengths produces a localized wave packet which is localized in space. To describe a particle in space and time, we introduce a wave function psi as a function of x, y, z and t, where x, y, z are the position coordinates and t is the time coordinate, which has three basic properties. Firstly, it can interfere with itself. Therefore, you will have interference and hence superposition. Secondly, it is supposed to be large where the particle is and small elsewhere, so that we can locate approximately where the particle is present. And thirdly, it describes the behavior of a single particle. That means that the wave packet that is being discussed will describe the single particle behavior. Now, let us discuss about the form of the wave packet, because it is imperative to know what the form of the wave packet is, as the extension or the spread of the position, that is delta x, and the wave number, that is delta k, both depend upon the form of the wave packet. And unless and until we know about these two spreads, we will not know how the uncertainty principle will behave. So, a typical form of a broad wave packet is shown in the figure. Note that a narrower wave packet is built up by a broad range of wave numbers k. In fact, the broader is the delta x in the wave packet, the narrower will be the range of the wave numbers, that is delta k. Conversely, a narrow wave packet, that is small delta x, will contain a large number of waves having a broad spread in wave numbers, that is a very large delta k. Now, let us again look at the figure. As you can see, the figure on the left hand side is a figure which is basically a wave packet, and you have on the y-axis the wave function, and along the x-axis you have the position coordinate. Here you can see that delta x denotes the spread of the wave packet in the position or the space terms. Now, the corresponding Fourier transform of this wave function with respect to the wave number k is given on the right hand side of the figure. The right hand side figure shows that for a given wave function, what is the spread delta k, or rather let us put it in this manner, that for a given delta k, what is the wave function like? And you see that it appears to be like a Gaussian wave function. Here again, from these two figures, it is important to understand that the larger the value of delta x, the smaller is going to be the value of delta k, and conversely, the smaller the value of delta x, the larger is going to be the value of delta k. So one has to be very careful in choosing what our wave packet will be, because if we take a very large wave packet, then even though we might have a precise determination of the momentum because of a small delta k, but we'll have a very large delta x, which means we will not be able to exactly tell what is the position of our particle. On the contrary, if we choose a pulse as a wave function in the position space, then the position of the particle would be determined quite accurately. But here, the Fourier transform in the k space will give us a very large delta k. That means that delta k will be spread quite large, and as a result, what will happen is that the determination of the momentum because of the delta k will become very difficult, and you will have a wide range of values which would occur in the momentum. In this sense, a balance has to be struck between delta x and delta k, or in other words, in choosing our wave packet, so that we are able to make a reasonably good approximation both about the momentum of the particle as well as the position of the particle. Wave packets in space. To understand qualitatively how a superposition of a small number, say only 3 plane waves, can produce a localized wave packet, let us consider 3 different plane waves which are given by the expressions phi 1x is equal to a as a function of k naught by under root 2 pi into exponential to the power I k naught x. Here k naught is the wave vector of the first plane wave, and a as a function of k naught is the amplitude of this wave, and phi 1 as a function of x gives the wave function for this wave. The second expression, phi 2 as a function of x, is equal to a k naught upon under root 2 pi into half into exponential to the power bracket open I within brackets k naught plus delta k by 2 into x bracket closed. This equation is the equation for the second wave, where phi 2 as a function of x is the wave function for this wave. A as a function of k naught is the amplitude of this wave, while k naught plus delta k by 2 is the wave vector of this wave. The third wave is given by the wave function phi 3 as a function of x and is equal to a as a function of k naught upon under root 2 pi into half into exponential bracket open I within brackets k naught minus delta k by 2 into x bracket closed. Here again a as a function of k naught is the amplitude, while k naught minus delta k by 2 is the wave vector associated with the third wave. From these three equations, one can see that the wave vectors that are associated with these waves are k naught plus delta k by 2, and k naught minus delta k by 2, which means that these three wave vectors are close to each other, and hence the corresponding amplitudes of these three waves are proportional to 1, half, and half. The superposition of these three waves gives the resultant wave function, which is denoted by psi as a function of x, and this wave function is equal to a as a function of k naught by under root 2 pi into exponential within brackets I k naught x into bracket open 1 plus cos within brackets delta k by 2x bracket closed. Thus, the three waves superimpose to give this final wave function, which is the wave function that describes a wave packet. Example of a wave packet. It is seen that the wave function psi x associated with the wave packet has a maximum at x equal to 0 for its amplitude. That is, the amplitude of psi x is maximum at x equal to 0. The reason for this is that at x equal to 0, all the three waves are in phase and interfere constructively. However, as one moves away from x equal to 0, the three waves are no longer in phase and the phase difference increases, with the result that the amplitude of the wave function of the wave packet, that is, modulus of psi x, starts decreasing when the phase difference between the three harmonic waves, that is, exponential within brackets I k naught x exponential bracket open I within brackets k naught plus delta k by 2 into x bracket closed and exponential bracket open I within brackets k naught minus delta k by 2 into x bracket close becomes plus or minus pi. The wave function approaches 0. This is when x is equal to plus minus delta x by 2, where delta k delta x is equal to 4 pi. Now we consider the Fourier transform of the wave function psi x. The Fourier transform f as a function of k is equal to 1 by under root 2 pi integral with limits from minus infinity to plus infinity psi x e to the power minus I kx into dx. Wave packet and uncertainty principle. A wave packet built from the sum of infinitely large number of continuous harmonic waves of various wavelengths gives the resulting wave function, which can be mathematically expressed as a Fourier integral of f as a function of k over the wave number spread dk, given by psi x is equal to 1 upon under root 2 pi integral with limits from minus infinity to plus infinity f as a function of k e to the power I kx into dk. It can be shown from the theory of Fourier transform that for the above equation, the spread or the difference between the wave number from the initial and the final values, that is delta k, is greater than or equal to 1 upon delta x, which is the spread in the position. Now, since the momentum of the wave or the particle is given by P is equal to h cross k, therefore the spread in the wave number can be represented by a change or a spread in the momentum values, and this spread in the momentum values is given by delta p is equal to h cross delta k. Using these equations, that is delta k greater than equal to 1 by delta x and delta p is equal to h cross delta k, we can write the final expression as delta p delta x is greater than equal to h cross. This is essentially the first form of the Heisenberg's uncertainty relation, which involves the momentum and the position, and which states that it is impossible to simultaneously determine the exact position of a particle as well as the momentum of the particle. The uncertainty in the simultaneous determination of these two quantities, that is position and momentum of the particle, being greater than h cross, where h cross is equal to h by 2 pi and h is the Planck's constant. Just like we have shown the uncertainty principle using the uncertainty in the determination of momentum and position of the particle simultaneously. Similarly, in an analogous way, the dependence of the wave packet in time, which is built from the superposition of harmonic waves of various frequencies mu or equivalently omega, which is 2 pi mu, can also be done. The Fourier transform of the wave packet is given by psi as a function of x and t is equal to 1 upon under root 2 pi integral with limits going from minus infinity to plus infinity, g as a function of omega, e to the power I kx minus omega t into d omega. Here, g omega is the Fourier transform with respect to the frequency of the wave function. We find that the spread in time delta t of the wave functions phi and the spread in frequency or the angular frequency omega, that is delta omega of the time Fourier transform, has the relation delta t is greater than or equal to 1 upon delta omega. Now, the energy associated with the wave packet having an angular frequency omega is given by E is equal to h cross omega, where h cross is equal to h by 2 pi and h is the Planck's constant. Thus, if delta omega is the spread in the angular frequency, then the corresponding spread in the energy associated with this frequency spread is given by delta E is equal to h cross delta omega. The above inequality, that is t greater than or equal to 1 by delta omega, and this relation of the spread in energy, that is delta E is equal to h cross delta omega, can be combined to give the second form of the Heisenberg's uncertainty relation, which is delta E delta t is greater than equal to h cross group velocity of a wave packet. Consider a wave packet which has a Gaussian form as shown in the figure. Suppose it has a maximum at the point x as a function of t, capital X as a function of t. If the position of the wave packet changes with time, the rate at which the maximum point moves is a measure of the velocity of the wave packet, that is, Vg is equal to derivative of capital Xt with respect to time, that is, d by dt of capital Xt, where capital Xt is the point which denotes the maxima of the wave packet. Here, it is interesting to note that why have we chosen the Gaussian form, or why are we so interested in considering a wave packet? The reason is that the wave packet has a Gaussian form and the Fourier transform of a Gaussian function is also a Gaussian function. Thus, by taking a Gaussian function or a Gaussian form, we ensure that the spread in the two coordinates which represent the relationship of the uncertainty in the Heisenberg's uncertainty relation, that is, either the momentum and the position or the energy and the time, will have a spread which is not very large. Now, as the wave packet consists of a group of waves having a range of wavelengths, we can write the wave function of such a packet as psi as a function of xt is equal to 1 upon under root 2 pi integral with limits varying from minus infinity to plus infinity fk e to the power I within brackets kx minus omega t into dk. In this expression for the wave function, f as a function of k is the Fourier transform with respect to the wave vector, and k, the wave vector, is associated with the particular wave packet. Expression for the group velocity. Looking at the expression for the harmonic wave represented by the wave function psi x t, we have that the wave function have values of k, that is the wave number, lying within a range centered about some value k bar, that is, the Fourier transform f as a function of k is assumed to have non-vanishing values only when k is very close to k bar. This assumption ensures that the angular frequencies omega of these harmonic waves will remain very close to omega bar, where omega bar is equal to omega as a function of k bar. Here, k bar is some kind of an average of the wave vectors or the wave numbers being considered, while omega bar is some kind of a average or a center for the spread of the wave number. Therefore, if omega k is expanded in Taylor's series around k minus k bar, that is, we have omega as a function of k is equal to omega bar plus within brackets k minus k bar into derivative of omega with respect to k with limits k bar equal to k. Using Fourier integral, one can show that the expression for group velocity is x prime t is equal to derivative of omega bar with respect to k bar, that is d omega bar by dk bar is equal to or equivalent to the group velocity. Using relations E is equal to h cross omega bar, that is the energy associated with the wave packet, and the momentum of the wave packet given by h cross k bar, we find that the expression for the group velocity agrees with the classical expression, which is d omega bar by dk bar is equal to derivative of the energy with respect to the momentum, that is dE by dP, and this is equal to d by dP within brackets p square by 2m, or in other words, the derivative with respect to momentum of the energy given by p square by 2m, and this gives us the final relation, which is d omega bar by dk bar is equal to p by m. Here, the group velocity denotes the velocity of the particle with which the particular wave packet is associated. Evolution of a wave packet with time. How does a wave packet evolve with time? In order to study the evolution of a wave packet with time, let us consider a Gaussian wave packet. F as a function of k is equal to c into under root alpha into exponential within brackets minus half alpha square within brackets k minus k bar whole square bracket closed. Here, the propagation variable has a Gaussian form with the width of the wave number, that is delta k, approximately equal to 1 by alpha about the mean position k bar. Writing the wave packet in terms of the wave function psi as a function of xt in x space or the coordinate space as a Fourier transform of the function f as a function of k, that is psi x t is equal to c into within brackets 2 pi alpha upon alpha square plus I h cross t by m whole to the power half exponential within brackets, that is bracket open, minus within brackets x minus I alpha square k bar whole square upon 2 into within brackets alpha square plus I h cross t by m minus alpha square k bar square upon 2 bracket closed. Performing the integration over the wave function psi xt, we finally get the modulus of the square of the wave function, and performing the integration over the wave function, we get the expression for the integration as psi as a function of x and t is equal to c into under root alpha into integral with limits varying from minus infinity to plus infinity e to the power minus half alpha square within brackets k minus k bar whole square e to the power I within brackets kx minus omega t dk. Evolution of a wave packet. The modulus squared of the wave function psi as a function of xt modulus whole squared is equal to 2 pi modulus of c square upon bracket open alpha square plus h cross square t square by m square alpha square bracket close whole to the power half into exponential bracket open minus within brackets x minus t h cross k by m whole square upon alpha square plus h cross square t square by within brackets m square alpha square bracket closed. The point to note is that it has a Gaussian shape and its peak is at x equal to h cross t k bar by m, or the velocity with which it moves is p bar by m, where p bar is equal to h cross k bar. Comparing this expression of the squared modulus of the wave function with the squared modulus of the wave function at time t equal to 0, that is modulus of psi x0 whole squared, we find that the spread of the wave packet alpha square is in fact replaced by alpha square plus h cross square t square upon m square alpha square. That is, breadth of the wave packet increases with the time as the time progresses and the wave packet evolves with it. Now students, let us summarize what all we have learned in this module. Firstly, after studying this module, we should know how the superposition of plane harmonic waves of different wavelengths or wave numbers can produce a wave packet localized in space. Secondly, learn an important criterion for localizing a wave packet describing a particle in space. Then, we also got to know that the superposition of plane harmonic waves of varying frequencies or angular frequencies can produce a localized wave packet in time. After that, we defined the wave velocity and the group velocity, and we saw that the group velocity of a wave packet is actually the particle velocity or the velocity associated with the particle which is being described by the wave packet. And we also showed that this is in agreement with the classical expression of a particle velocity. Finally, we analyze the evolution of a wave packet in time and show that the spread of the wave packet increases with time. Thank you.